Welcome to today's talk between HighRes Biosolutions and Tetrascience. The talk is titled Latest Advances in Dynamic Scheduling Software for Lab Robotics and Data Integration. I'm Mike Tarselli, and I'm the CSO of Tetrascience. And joining me is Ira Hoffman. Hey, Ira.
Hey, Mike. Thanks for the intro. My name is Ira Hoffman. I'm the CEO of HighRes Biosolutions. And what we're going to talk about today is the integration of laboratory automation with data pipelining. We'll start off with introductions. We'll move into a brief HighRes overview, who we are, what we do. Do the same for Tetrascience, provide you a brief demo of how these systems actually work together, seeing the data being output from systems as we run, and give a brief summary. HighRes Biosolutions is a systems integrator. We build tailored lab automation solutions using the best devices and software for any workflow. We pride ourselves on being an agile and innovative provider. That's not just in how we behave, but also in our products. So what you see on the right are a set of our docking stations, which lets you change the instrumentation around your core automation systems. We're established in 2004, and we have about 170 employees today, headquartered in Beverly, Massachusetts, with a European office in Manchester, UK. We've got over 250 system installations globally, and we're an ISO 9001 certified company. As with a lot of lab automation, we started in the world of drug discovery and compound management, but lab automation world has really exploded since then. And we're involved in any area that benefits from using lab automation, which is really for higher throughput, error reduction, or uniformity. So here you see some of the sample areas we work in: genomics analysis, sample management, and obviously this year, a pretty big explosion in COVID-19 research and testing. From our perspective, we think about the basic lab automation workflow by this picture, right? You start off with some experiment design, and you need a physical and efficient format to support this, exploring this space. And these are, plates or labware, right? And so you lay your samples out into these. Then you need some equipment and people to run these experiments. You need this intuitive control software, which is our platform called Solario, to simplify the process of designing these and executing these workflows. And then the last step is collecting the data and then analyzing it to facilitate decision-making and next step planning. This is the basic design, make, test, analyze lifecycle you see in most of research today. And this is how our products and our platforms support that workflow. So some of the challenges that we see in research today are the following. These systems can be large and complex, and I just think that they're inherently complex. A lot of our strategy in products is designing platforms and software that simplifies and eases that process for the scientists. Our objective is to let scientists focus on science and not the nuances of a large robot. Some of these complexities can be setting up the system. You have, a 30 device system that have a lot of configuration. You have to load your reagents. You have to make sure you have sufficient seal. That's a challenge, because if you forget to do something and you stop your run in the middle, that's an expensive, time-consuming operation. The scientists have to understand the conditions of the experiment. These are large, multi-parameter experiments. So they have to have a strong understanding of all of that to be able to run successfully. As you'd guess, there's a lot of computing on here, a lot of computers, a lot of devices, information flow across systems. This typically results in complex IT configurations, which is the last thing a scientist wants to deal with while they're trying to perform an experiment. You've got a challenge of data file formats. Every instrument produces a different file format. How do they then normalize this and analyze their data in a consistent fashion? How do they annotate their data coming off of such a system? I think in the traditional world, you just have a file. You don't know anything about its genesis, and the scientists to manually annotate it. What if that could be added automatically? And the last bit is, as these instruments produce these files, a lot of times scientists actually have to go copy it, move it, rename it. Maybe they forget it, place it in the wrong location. A lot of these challenges result in loss of time, loss of data, or inaccurate information. And we believe the software that we build and platform we build enables that, as well as enables us to integrate with other software tools, which really streamlines this whole process. So to address some of those, we've built a lot of features and functionality into Solario. So for instance, Solario can provide setup assistance through pre-run checklists. We know what you need to do. The protocol author can describe the setup sufficiently and algorithmically. So we walk you through how to set up the system. We have a set of APIs which let us integrate with other types of virtual assistants, such as like a lab voice, which you can say, hey, Solario, where do I put these plates? And it will tell you. Or a visualization tool like Artificial, so you can actually visualize where in the system you need to load the plates for this order. The more we can help guide the operator to run successfully, the more likely it is to run successfully and the more they can focus on their science. Our modern API set on the incoming side and the outbound side simplify IT infrastructure. Historically, you have to deal with things like Windows file shares and wonky Windows permissions to gain access to data, which is the last thing you want to do. Using modern RESTful web-based API technologies, that really simplifies that process. Solario also automates the data. So as you're running, we'll just stream events about what is happening, and anyone can pick that up. And you'll see in this demo how Tetrascience gets notified of that, and not just only grabs the raw data file, but then starts to process it. Solario can describe its capabilities to others. So what does that mean? If you want someone upstream to be able to place orders, they can just ask, hey, Solario, what can you do? Great, here's this protocol, here's its capabilities, here's these parameters. So that means it's much easier for these upstream systems to dynamically inspect and integrate with Solario. As you're running, Solario provides automatic annotation. You get a full context of what's happening on the system, current conditions, all of the metadata passed into the order. That's included with this data output, so you not only get that raw data file, but the context in which it was created. This is really going to really allow and support, we think, the future of AI and ML, because not only is that data useful, but the context is going to lead to improvements in operational performance and analysis. And a key part of our strategy is to use modern discoverable APIs and be very API forward. We believe that being more integratable and easier to integrate, it will create a better opportunity for more complex integrations with different platforms. And so with this strategy, we think that our software is really going to enable and simplify closing this loop of the design, test, analyze process. So with this stack, I'm just walking through essentially where the API sets live in Solario. So you've got the design side, which is typically external software. We have ordering APIs to allow you to place orders in a variety of formats. And then as we run, we can publish data using a modern publication mechanism to any analytics system. This really creates a very nice connected workflow from any design system to execution to analyzing in any system. And so with that, I'm actually going to hand over to Mike to talk about Tetrascience.
Thanks, Ira, for passing over to me. This is the Tetra Data Cloud overview, so you can see how we pick up orders from Solario or indeed instantiate orders to Solario. So real quick about the Tetra Data Platform. We break the world into what we believe is data sources and data targets. Our viewpoint is that the current landscape of the pharmaceutical, biotech, and ancillary industries data management is a little bit fragmented. So we see things that produce data on a routine basis. These include contract research organizations, so facilities outside of your control, instrument and control software for general purpose instrumentation, mass specs, DSCs, HPLCs, sensors and facilities. So this could be heat sensors, temperature sensors, airflow, whatever have you, a refrigerator sensor, or informatics applications that are producing data to monitor a process or to give you real-time analytics. We then see those moving to data targets on the right-hand side. These are your ELN and LIMS, your electronic laboratory notebook, or your order management and sample management systems, a data lake and data warehouse where you'd like to store the data eventually, your data science and visualization applications, Tableau, Spotfire, Streamlit, and of course, as we're going to show in this demo, robotics and control software such as Solario, so that you can actually use the Tetra Data Platform to instantiate these type of automation cascades. So today, we think of this as a spider web. A little bit manual in between. People often have to trigger these processes, or at worst, they're moving files from place to place through a USB stick or through email. And it's often point to point. So you have decided to connect your instrument and control software to everything, or you've decided to have your sensor streams move to multiple different sources. We think that that's actually an inefficient way to go. We think perhaps you could be more effective if instead you had a everything to one to everything motif. So what does this allow you to do? This allows ingestion into a cloud. And again, we write the Tetra Data Platform not as our cloud because it can be deployed inside of a private cloud inside of your company as well. And we think of this as being connected by connectors and agents. A connector is a direct piece of software that reads or listens to a system such as Solario. And agents, of course, are Windows or Linux-based that allow integration on a routine basis. So these connectors and agents collect instrumentation data. They bring it in to a cloud. They then extract, decorate, and validate. Perhaps your data needs pre-processing. Perhaps it needs metadata appended to it from another system, or perhaps you are running under a controlled process and you need to validate to ensure that this is the same kind of data that has been shown in other processes. We then harmonize it and prepare it. This is no secret sauce. This is literally to JSON, JavaScript Object Notation, which is a dominant form of collaboration and software hierarchy on the web. This is a fairly open system, and so you can, of course, relay these and reuse these. So if you've developed a data schema for a mass spectrometer or for a robotic system, you can believe that you can probably port that with very little customization effort over to a similar instrument from another vendor. And finally, we create data applications such as in Streamlit, Jupyter, or other systems in order to let you see all of the data. We also produce, of course, SQL and API pipelines that allow data export of this harmonized and extracted decorated data over to your system of record. So again, this seems like a lot of hand waving, but I will say that what this in the end allows scientists to do is look in these data target systems and say, where is my data from this experiment? And all the data here has been aggregated, harmonized, and moved to that system. So you can basically open up an ELN or open up a visualization and know your data will be real time and updated. If you are a person from the IT side, of course, this is probably wonderful for you. You can automate processes, which reduces the errors and saves time on your automation. You can centralize this. It's in a cloud. You have raw files, processed files, and data schema, so you know where everything is and lives, and it will be good for you into the future. You have good data integrity. The data is harmonized. Again, you will see very few inconsistencies between vendor instruments or between different file formats because we have put this all in this JSON hierarchy. You'll see this later in the demo. And then again, it's prepared so you can do AI and data science. And of course, if you're a scientist watching this, you should know that your accelerated time to insight allows you to do things like AI machine learning applications and also have always accessible data. It's real time, it's updated. It's always up to date because we've pulled it multiple times. Automagic integration. Should you wish to look for data, you don't have to say, oh, I don't think that my cascade completed or I think the instrument failed. If it has run and you have set up a pipeline, it's going to be in your data target system. And worst, it will be in the cloud, so you can always go back and get it again. And of course, pioneer new technology. Should you wish to integrate new instrumentation or new scientific developments into your work stream, you can do so. You simply have to call up Tetrascience and say, do you have this connector? For example, do you have Solario automation integrated? And we'll say yes. So you're encouraged to go buy that new instrument. And then finally, you can achieve deeper and unexpected insights. Perhaps you've never thought about this, but maybe a specific column in your cascade is doing something to a substrate. Maybe you have a cell culture that you need real-world evidence to figure out whether something is going wrong or not in your biology. There's operational metrics, there's scientific metrics, there's several elite level. So what you're about to see in this demo is, as Ira has alluded to, you're going to see some API control that allows you to go through an automation feedback loop. At this time, you're going to see a step one, an order brokering and instrument control. You're going to see HighRes initiate an order in Solario, and you're going to see data being run through a collection, through a test screening assay. You're going to see through the Solario integration, it being passed back to Tetrascience, and then you're going to see a pipeline run on it to unzip each plate and to relay the data back so that you can, again, create a new run or order through Solario from the Tetrascience system, aka allowing you to go around and around this automation loop such that a human only need be involved here at the front, and technically the system could make decisions and can help you instantiate automation around to continually refine your process, to investigate a new parameter, or to perhaps prepare yourself for an AI and machine learning driven effort. So how does this work? In reality, what you're about to see is you're about to see something where you have a chain of events that is happening and is being picked up by both sides through the API. HighRes, in the first instance, will be initiating an order to its automation. Data will come back from that order, and then Tetrascience will be listening for a file to be passed back. This zip file will come back, it will be unzipped and verified into plate data. You'll then see the automation go around where an order is instantiated in Tetrascience. The event is posted and an order is created in HighRes, it goes back through the automation, data comes back, a listener on the Tetrascience side says, oh, my event is finished, brings back the file, unzips, and again, you have plate data. So you'll see both sides of that automation cascade. All right, so let's start the demo. Ira, over to you.
Great, thanks, Mike. So here we are in a Solario environment. If you want to get a full demo, we're happy to provide one to you. We're in booth 23. Our great team over there can give you a full walkthrough, answer any questions you may have. So what you see is our scheduling software. I'm just going to walk you through briefly what we have here. So this is the main dashboard. I'm actually going to flip over and take a look at the protocol we're going to run today. This is probably the world's simplest assay, and so it's aptly named my favorite assay. What we have going on here is you've got a plate here, and the assay plate coming out, dispense reagent, transfer some sample into it, incubate and read. Great, wish all assays were that simple. The magic happens here when we actually read. So we're actually capturing and collating this data, creating events to consumers. Another thing that happens is when we finish the run, we'll package all of that data with a nice metadata descriptor file. So you get that annotated individual files with a full context of the run. So what I'm going to do now is actually just create an order for that protocol. So this is Solario ordering. I'm going to choose my assay. I'll use an order template, which really streamlines the ordering process. I just need to indicate the batch number I want to run. So let's run 5 batches today. Go ahead and place that. Great. That's where I put my plates. So now I'm going to switch over to the run screen once I save my order. So on the run screen, great. Here's my assay. Let's go ahead and start this up and see what happens. So I choose start run. And at this point, the software is running fully simulated. I don't have a system here. So all the operations are happening really quickly, which is what you see in this queue here. Each plate out on the system performing its liquid transfers, performing its moves. This is a message log of what's going on. These are all the instruments. As all these operations are occurring, all this data is being captured. All of the operation data as well as actual measurements. So at this point, we just read the last plate. And so what Solario is doing is collecting all those individual data files, packaging them up, and has created an event and sent it to all the subscribers of our data production. So at this point, if we flip over and look on the other side of the pipe, some of this data should have appeared in the Tetrascience queue. So let's flip over and see what we find.
All right, Ira, thank you very much for that. And we now see, if you look at the refreshed files in our environment, you are now seeing Ira's order come through. In the magical world of this recording, we did on January 22nd at 8:53 instantiate this order, and the order finished in record time. So we see not only the zipped bundle, the data package that we were listening to for the event, but we also see the JSON. You'll remember in the little preamble, we talked about this being a consistent and harmonized way to look at this data. So if you look at this JSON, in fact, what you see is that you are looking at a very well annotated, metadata-rich perspective on your run. And of course, Ira passed me back an order called 16646. So here's 16646. But that's not all you get. You also get the name, the barcode, the type of labware that you're using, all the device drivers, the state, who ran it, when they ran it, the operational order IDs, the start date. Every single bit of the metadata you need for this run is here. So if you have a very different approach to your lab automation, and you wish, instead of just looking at the data that is output on a plate, to say, all right, how is this particular operator performing? Or what's this particular instrument doing? Or was there an error in that plate? Or perhaps you look at the different statistics that are coming out of multiple runs and you say, oh, you know, this HighRes Ambastor 01, we should look at that and investigate that as a target. You can do that because this is such a metadata-rich system that's passing to us. And of course, as you see here, he has a zip package that's passed to me. So if you unwrap that, you will see actual plate data being passed back. And that plate data, of course, has responses, times, columns, rows, so that you can start to model data, create visualizations and representations of your data, and learn both operationally and scientifically. All right, now as promised, we said we were going to be able to look at this from the Tetrascience side and create a remote order. So what I'm showing you in here is that let's pretend that you were living inside of the IT environment at your pharma or biotech, and you have Linux boxes in which you can install agents and connectors, and we've chosen to install the Solario connector here on this box. What this allows us to do is this allows us to actually start up in the background, and I'm doing a little bit of demo magic to create an order remotely, sending out a command through the Solario services and creating a new run. So what I've done in the background is I've started up a new run, and we will go back over to the searched files, and we will refresh, and we'll see, in fact, that I have, oh, sorry, that's the plate processed from Ira's last run. So that's the 5 plates that he promised you would be coming from his assay 16646. But if we refresh, we're going to see that a new run is actually starting to come in. New data packages are going to come in. Oh,
just finished, Mike, so you should see it any second.
It's just finished. Excellent. Thank you very much. That was the fastest automation in history. All right, 1 minute. Excellent, there we go. So really in literally real time, and to prove to you that we're not just faking this on the demo, I'm going to download that zip and open it. And I'm going to actually bring back up one of the files that's out of that zip. So here is the plate data from that particular run. So you will see, of course, that new plate data has been generated. And of course, each of these has developed a new JSON. So that's, again, the data schema that we've talked about. And if we download this and open it, we will identify that not only is it a new run, 16647, makes sense, the next sequential order, but again, it has all of the same rich metadata that you had before. So what we've shown you here in this demo is we've shown you both initiation of an order in Solario and then picking it up on the Tetradata platform, as well as looking at those analytics, coming back around instantiation of a new remote order from the Tetradata platform, and then the fulfillment of that event and order from Solario.
Thanks, Mike. That was awesome. I wish all the automation ran that quickly and smoothly, but it was great to see. I think some of the key things we saw there were the ability to both start from the robot side, so as you're in the lab, actually start an experiment as you usually would, but to also start from the analysis side and drive automation automatically through APIs. So as you can see, you can have person-initiated or software-initiated runs on the platform. And both of those are kind of parameterized runs where the parameters could either be specified by the user, or whatever analysis you do can then define the next set of parameters. That means you can now have software driving you intelligently through whatever parameter space you want to explore. And I think this is really getting to the heart of what this type of integration is trying to accomplish, is this automated feedback loop actually being realized. And it really requires, the automation exposing itself as parameterized capability. So that way anyone can place orders against it and then publishing that rich annotated data. And that's what you saw. And then you have these smart tools monitoring, picking up, being able to perform automated analysis, storage of that raw data, then the smarts to make the decisions about what to do next. Do you want to look at a different compound? Do you want to synthesize a new compound? Do you want to run a different assay? And then to drive the next order. And that's what you just saw in that demo. Starting from automation software, capturing data, doing some analysis, creating the next run, and then driving the loop again. So we believe that this set of capabilities is really going to be pretty powerful as folks understand what you can do with it and start to apply it to their research areas. Which leads us to where we think we will go in the future with this type of capability. So from the HighRes perspective and other ways we think about, you can use tools like Tetrascience to understand, analyze, and optimize your automation. Are we looking at some of the following areas? One, monitoring uptime. So again, automation is comprised of a large collection of machines, and those are real-life machines. They have failure modes, they have failure points, they have certain things that cause them to not work as well. Why don't we monitor that and prepare for it and proactively say, hey, let's pay attention to this piece? We can use it for operational information, not just scientific information. A lot of automation platforms run as factories, right? That run the same thing over and over. And good factories will just apply continual improvement. And one way you do that is data-driven analysis of performance. So by having this automated analysis loop, you can actually see where you're not performing well and actually drive automatic adjustments to process parameters through this mechanism. So not just scientific optimization, but also operational optimization. So we think that not only the scientific data, but operational data will be used in this type of analysis. But we see this going in a lot of different directions, and it has a lot of powerful capability. And so with that, I'm going to hand over to Mike and talk about the future direction that Tetrascience is considering.
Yeah, certainly. So the Tetra Data platform is certainly playing in the same world, only on the back end of it, right? We're going to leave the running of the automation, the control of the robots over to folks such as yourself, and we're going to take that data and do what we can do best. So at the bottom of this slide, you're seeing new visualizations that can be generated. So that plate data that I showed you in raw text format, of course, you could put that in a much more beneficial way to your scientific end users for their project meetings by saying, for example, on the left, what does my automation uptime look like on a month-to-month basis? Or on the right, let's construct a heat map from the raw data on a plate. And of course, these can be done on the fly in your visualization browser of choice. We again have harmonized this data. So when you want to start up a machine learning model, you can certainly do it because you don't have to worry about that curation and cleaning that often has to come from moving different data sources into this model. There's integrated experimental metadata, right? Iris spoken about this parameterized experiment and about this metadata-rich file that comes back. Well, since you have that, you might as well see and ask the question, when I run this cell line, does the temperature system timing matter? Or when I run this particular construction of this particular pharmaceutical intermediate, does it matter when I've run the injection on the column? Or does it matter when I've taken the analysis? Maybe it's finished faster than you think. The only way to know is to capture all the metadata. And then finally, again, we can integrate this with tracked sensors and process logistics so that instead of just thinking about this in a research and development context, we can extend this into a manufacturing motif. So if you have a process analytic technology that's monitoring reactors or monitoring real scale robotics, you can certainly be inserting this data in real time with continuous data from temperature, light, pressure sensors to augment the experiment you're already doing. So thank you very much for listening to us. I'm going to leave it to Ira to close out.
Thanks, everyone. Thanks, Mike. Hope you enjoyed the talk. Please feel free to come see us in our respective virtual booths this year, ask any questions, and bring your great ideas of how we can apply these tools to solve your problems. Thank you.
Thank you.